Welcome to Lesson 40, Rutherford Scattering and Types of Radiation. This is the final block of the course, Nuclear Physics. Here's the plan for today. Before Rutherford, the accepted picture was the plum pudding model, electrons floating around inside a big spread out ball of positive charge, like plums in a pudding. No nucleus, just a diffuse blob. Rutherford aimed to disprove this idea by experiment. So what he did is fire alpha particles, which are positively charged, at a very thin sheet of gold foil and watched where they went. 3 things happened. 1. Most of them sailed straight through, completely unaffected. 2. Some were deflected by small angles. And 3. A very few, remarkably, bounced almost straight back at him. Now read those results. Most passing straight through means the atom is mostly empty space. Some being deflected means there's something charged in there. And a few bouncing right back means there is something very small, very dense, and very positively charged for them to hit head on. A concentrated central positive nucleus. And that killed the plum pudding stone dead, because a diffuse blob of charge could never have thrown an alpha particle back the way it came. And you can even get the size out of it. If only about 1 alpha in 10,000 comes back, then the nucleus must present a very tiny target. That hit rate tells you the ratio of the nucleus's diameter to the atoms. It turns out that the nucleus is something like 10,000 times smaller than the atom. The atom really is almost entirely empty. Now the 3 types of radiation, and this table is essential. Build it into your notes. Alpha is a helium nucleus, 2 protons and 2 neutrons. It's big, heavy and doubly charged, so it smashes into everything and ionizes fiercely. But precisely because it interacts so strongly, it loses its energy almost immediately. It travels only a few centimeters in air and is stopped by a sheet of paper or by your skin. Beta is a fast-moving electron or positron. Much smaller and lighter, so it ionizes less, but it penetrates further, about a meter of air, and it takes a few millimeters of aluminium to stop it. And gamma is a high-energy photon. No mass, no charge. It barely interacts, so it ionizes weakly, but it travels a very long way and you need thick lead or concrete to stop it. Notice the pattern. The more strongly something ionizes, the less far it gets. Ionizing power and penetrating power run in opposite directions, and that's not a coincidence. Ionizing is exactly how the radiation loses its energy. How do we detect any of this? The Geiger counter, and it works on exactly the property we just discussed, ionization. Radiation enters the tube and ionizes the gas inside it. The positive ions drift towards the wall and the negative electrons towards the central rod, and that movement of charge is a pulse of current, which you hear as a tick. More radiation, more ticks, and because all 3 types ionize, it detects all 3. Finally, why is this dangerous? Because ionizing radiation damages cells, and in particular damages DNA, which can lead to mutations and cancer. And there's a contrast worth understanding rather than memorizing. From outside the body, alpha is nearly harmless. It can't even get through your skin. Beta and gamma are the dangerous ones, because they penetrate and reach your organs. But get an alpha source inside you, swallow it or breathe it in, and it becomes by far the most dangerous of the 3, because now there's no skin in the way, and all that ferocious ionizing power gets dumped straight into a small volume of living tissue. Alpha, harmless outside, deadly inside. That reversal is a classic exam question. And that's the end of the video. Thanks so much for watching, and check out my tutoring page below.